Hello and welcome to item 7 of effective Java, and this item is about obsolete references. So item 7 states that eliminate obsolete object references. And if you're familiar with Java, and you might get the impression that Java you don't really need to do basically memory management in Java, but that's not entirely true, and this item is mainly about that. So Java is a garbage collector language, which means it does some sort of automatic memory management. And this happens behind the scenes. So behind the scenes, we have another application as part of our Java runtime, which is called garbage collector, right? It's part of the JVM itself, part of Java runtime. And it just traverses the heap, basically, and examines the heap and then see which objects are no longer references on the stack. And it gets, obviously, garbage collection and memory management gets complicated when you are especially dealing with multi-threaded application. That's why it seems almost like magic when you first experience it, because if you have done any coding in C++, mostly legacy C++, obviously in the modern C++ with the smart pointers like shared pointers or unique pointers, things have become easier. But at the end of the day, it's painful to deal with your memory management. And if it happens automatically behind the scenes, you almost feel like it's magic. It can easily lead to the impression that you don't have to think about memory management in Java, but that's not quite true, or that's not entirely true. Otherwise, this item wouldn't have been existed, right? Sometimes a program has a memory leak, and we will see an example that this is typically the case in Java when a class manages its own references, its own memory. Sometimes a program has a memory leak, which can silently manifest itself as reduced performance due to increased garbage collector activity or increased memory footprint. Now, this garbage collector activity is about the pause times that the GC has to incur on your Java heap so that it can mark your Java heap, mark the objects, and then figure out how to compact also. So usually the garbage collector moves objects around in the Java heap so that it compacts the memory, everything. So the garbage collector, one of the jobs is to make sure that there is a least amount of fragmentation in the Java heap, because fragmentation is bad. Whenever you want to try to allocate new objects, if there are fragments that don't quite fit the size of your object, then you can't use them. But if the heap is already compacted, then first of all, the JVM knows what is the starting address for allocating new, and it knows that it's completely free. There is no fragmentation after that address. So it makes allocation easier, but then you have pause times in your application so that the GC can work. In the latest version of the JDK, Oracle JDK, for example, they have added ZGC or zero GC, which means it has extremely small pause times, which is very good. So you don't really need to worry about the pause times of the GC for your application. But it also works with very large heaps. But each GC has its own benefits and drawbacks. So you have to test different GCs like G1 GC or ZGC or any other type of GC that is provided as part of your Java build to see which one works best for you. In extreme cases, such memory leaks. So memory leaks means the garbage collector cannot claim that object reference even if it's not being used anymore. So memory leaks can cause disk paging, which means now there's a swap happens between RAM, right, and your hard disk, and even program failure with an out of memory error. So the JVM just gives up. It says that I cannot allocate more memories, and then it quits or crashes. But such failures are relatively rare. Obviously, JVM kind of dynamics or basically manages the Java heap dynamically, which means when it starts, it grabs some memory from the operating system and it starts allocating using that memory. If it feels that the garbage collection is not helping and the amount of memory is not enough, then it reaches out to OS again and asks for memory. And obviously there are flags for the minimum amount of memory to start with and the maximum amount of Java heap that the JVM is allowed to use. You can always set these flags at runtime where you're running your Java application. An obsolete reference is simply a reference that will never be dereferenced again. And so this object is already created and initialized on the heap, so it's basically taking some space, but there is no reference on the stack that is referencing this object. So this object logically should be garbage collector and the memory should be reclaimed, but this doesn't happen. And so the problem is that there are objects that can have all the other objects. For example, an object array. So object array is still an object, but inside of it, it also holds references to other objects, right? So if I don't need one particular object in that array, as long as the object array is still alive, then that particular object inside the array that is not being used is not going to be garbage collected, right? And this is bad because this means there is a reference inside that array that is pointing to that object, but we don't care about that object anymore, right? So the classic example is any type of data structure, because the data structure, any type of this data structure manages its own memory, right? So for example, a stack or array list, these are dynamic data structures, so they can grow and shrink dynamically. But then the problem is that they're usually backed by some sort of other data structure. Array list can be backed by a primitive array or an object array, or we know that we also have linked list. It's just backed by objects of type node. But for now, let's assume that we're looking at a stack or array list, right? Array list is easier. A stack is also easy to understand. What happens here is that if you push items into the stack, then at some point the stack goes out of space, right? So you kind of need to grow it. Or even if you don't grow it, then what you can do is just throw an exception saying, okay, a stack is full, which we don't typically want. So we want these data structures to have some sort of dynamic growth and dynamic. But when you grow it, the question is, how do we shrink it? And the answer is that the most efficient way is to never shrink it. So if I double the size of the stack and then somebody starts to pop stuff from the stack, if the stack backed by an array, all I have to do, I have to move the pointer that is pointing to the top of the stack down, right? I don't need to really remove or resize that array. That's bad in the sense that there are also still objects in that array that we don't use, and that's some sort of memory leak. And obviously the book suggests that just change those objects to null, which means there is nothing really referencing them. When you set the reference to an object to null, it means that there is no reference on the stack. There is no pointer to that object anymore. So that object can be in fact garbage collected. So this item is about this basically memory leaks happen mainly when you're dealing with arrays of objects, some sort of data structure that holds a set of other objects, right? And so memory leaks in garbage collected languages, more properly known as unintentional object retentions, are insidious. So sometimes you don't notice them, or most of the time you don't notice them unless you go do some sort of profiling. So be careful. If an object reference is unintentionally retained, you don't null them. Not only is that object excluded from garbage collection, because the whole philosophy of object collection is that the object is reclaimed only if there is no active reference or a live reference to that. But if there is, then it's not going to be touched by garbage collector. Not only that object excluded from garbage collection, but so too are any objects referenced by that object, and so on. So if you have an object array, for example, and it holds a couple of objects, and as long as there is a reference to that object array, all the objects inside that array are also alive, and they're not going to be reclaimed by garbage collection. The fix for this sort of problem is simple: null out references once they become obsolete. Now, people used to do this in finalizers, but again, finalizers are obsolete, so don't do this kind of stuff in nulls. Finalizers are deprecated. So let's look at the Java util stack. So it has a pop. So let's say a stack is backed by an array, right? An object array. And what happens here is that when we pop an object from the top of the stack, it gets the reference to that top of the stack object and returns it, right? But then it has to shrink that array, because now the top item is not being used, which means logically it has to be removed from the stack. However, instead of creating a new array, because you cannot dynamically change the size of a object array, right? You either have to allocate a new array and then copy whatever items you need, or you just move the pointer that pointing to the end of the array down, right? So you still keep that array, but you just move the pointer. And what it does, so it gets a reference to the top of the stack, the end item in the array, returns it, but then it has one extra method, remove element at len -1. Len -1 is the end of the array or top of the stack. And what happens here is that it just sets the element count, the pointer. As you can see, it reduces the element count by 1, and then it sets the last item, which was this object reference that was returned, to null. And it also has a comment in the JDK saying that to let GC do its work, which is exactly item 7, eliminate obsolete object references. Because when somebody pops it, this array, there is no way to delete one particular item in an object array unless you just set it to null. And null means, hey, there is no reference to that object anymore, and so that object is truly not being used anymore. So go ahead and do the GC, right? To let GC do its work. So nulling references that are not being used is very important in terms of if you have them in some sort of object array. And the book continues by saying that an added benefit of nulling out obsolete references, and again, these are references that we're not going to use them. So these are pointers to the Java objects on the heap. We are not going to use them, but then we have to kill the references themselves by nulling them out, so that the garbage collector realizes that there is no pointer to those objects on the Java heap, so it can reclaim the memory. So an added benefit is that if they are subsequently dereferenced by mistake, and again, the book uses the terminology dereferencing, which basically when we have a reference in C++ terminology, we dereference the pointers, right? Using the asterisk operator. In Java, there is no such thing. But here, the dereferencing, the terminology just means that if you try to access any field or any method of that object using this reference, if a reference is nulled, right? If you try to access any method on that null, there is a null pointer exception. Now, in the recent version of Java, for example, since JDK 14, they added very nice flag to the JVM that has very nice details of where that null pointer exception is happening, right? I mean, you can say that this should have been named a null reference exception, not pointer, because Java is all about references instead of pointers. But I mentioned before that references are just glorified pointers. Basically, what it means is that they're more like the actual references in C++, right? So there is a subtle difference even in modern C++ between a reference and a pointer. If you null out a reference and later on try to access that object, any field or any method, you get the exception, and it's a runtime exception, it's a null pointer exception. And if you use the flag show code details in exception messages, it tells you exactly where the null pointer exception was triggered. And this is a Boolean flag. If you're not familiar with the JVM flags, Boolean flags have plus minus. Non-Boolean flags don't have this plus minus. Instead, you say whatever the flag is equals to the value. So they're more like key value pairs. So key equals value. Boolean flags are plus minus. If you want to turn something on and off, for example, if you don't want this, you set the minus sign and it tells the JVM that, hey, turn this off. So in summary, nulling out object references should be the exception rather than the norm, right? You shouldn't go around and null everything, especially avoid finalizers or avoid doing this kind of nulling references in finalizers. That's a very bad idea, and it's not necessary. And the JVMs get more and more basically smart and intelligent about this kind of problems. They try to add more and more optimizations inside the JVM. So the JVM gets better and better and managing this kind of faults. But again, these are the faults that eventually the person, the developer who writes a library is responsible for. Generally speaking, whenever a class manages its own memory, and we mentioned that this is more about data structures, right? Because remember that in any language, especially Java that we're talking about, the Java language doesn't guarantee the existence of data structures, and the core Java never guarantees that, right? So if you read through the Java language specification or any specification regarding the language itself, because people view data structures as an additional library, right? Java language guarantees the existence of arrays, primitive arrays or object arrays. This is, or basically an array of references or array of primitives. This is what the Java language guarantees, right? But then data structures are libraries that can be backed by any of those arrays. For example, an array list can be backed by a basically array, right? An array of objects, array of references or primitives. A stack in Java language can be backed by an array list or just a primitive array, right? So that's about data structures, and the data structures is about a group of or basically a collection of objects or references, and then the class itself, such as in a stack, is responsible for managing its own memory, which means it handles how the objects are not being used anymore, push something into the stack, pop it out of the stack, this kind of stuff, right? So the programmer should be alert for memory leaks, and again, this is mostly about objects or classes that manage their own memory in terms of an array of objects, etc. So more than one element is involved in terms of data structures. Another common source of memory leak is caches. Sometimes you want to cache something, but at some point, at some later point, that cache is not necessary anymore, so you're just reserving extra memory and nobody's using that. Let's say you have an object that caches some stuff, but at some point that object actually goes out of the scope, right? And until that object is dead, then the cache is still alive, even if nobody uses that cache anymore. A third common source of memory leaks is listeners and other callbacks. And again, callbacks are also very important. We know that in any GUI programming like Java Swing or Java FX, etc., we use a lot of callbacks in terms of listeners. And the problem with callbacks is at some point, listeners and callbacks should be deregistered. And this is a pattern about observer pattern in general, which means you register some listeners, and if some event happens, all these listeners, basically something gets fired, right? You fire an event, and then all the listeners get notified when that event is occurred, right? Is fired. But then the problem is that listeners are usually just interface, so objects. A listener, you just say new mouse motion listener, for example, or new keyboard listener, for example. You're creating objects, right? But at some point you probably need to deregister them if the object that is we assign listener to goes out of the scope. Again, this is important. Whenever you have a structure, a class that manages other classes, and this is more about composition, right? Then you kind of need to have this in mind, this item, obsolete references. So okay, let's go to Eclipse and try first looking at this new show code details in exception messages. So in Eclipse, I'm going to create, in my project, I'm going to create a new package. Let's call this item 7. And I'm going to create a class, let's call it test1, and I want to have a main method. And note that in Eclipse, in the most recent versions of Eclipse, so let's do a just sysout hello, and what it does in Eclipse, when I run this, it actually creates a run configuration, right? And this is my run configuration, and so when I go to run configuration, it shows the package 7 item 7 test1. This class, the main method of this class was run, and these are the arguments. And notice that in the most recent version of the Eclipse, it already checks this -xxs plus show code details in exception messages. What this means is that it tells you if an object is null. So for example, I can say a string s is null, right? a string b is s dot to lowercase, and then sys out b. Now we know that here this is going to throw a null pointer exception. So let's see this in action. Let's run this, and it throws a null pointer exception, and it can also gives you very nice detail of what's going on. It says that cannot invoke a string to lowercase because s is null. So it tells you exactly which variable was null, so that this null pointer exception was happened. So this is very nice feature. Obviously, if this string is not null, let's say Bob, and then this is going to work just fine. But then if it's null, then this is going to throw a exception and gives you very nice methods. If I turn this flag off, you show code details in exception message and run this, it just it is still interestingly shows the detail, which means that this flag is by default on the JVM, right? So it looks like this is the default thing. So we can try this by saying -xx minus show code details in exception messages. So I'm using a minus sign, which means try to turn this flag off. Let's see what happens. And now it just says a null pointer exception was happened. It gives you any details of which variable was actually null, right? And again, this flag is by default, it's a Boolean flag, and by default, even if you deselect this in Eclipse, it's by default on the plus sign, which means it's by default turned on, and which gives you very nice details of what happens, right? It says s was null, s, and you know where. And let's create a public static void method, public static, let's say a string, get s, public, and then return null. So we're returning a null, and instead of assigning s to null, we say that get s. Let's run this again. And it says cannot invoke a string because s is null. So it still recognizes that, but instead of doing that, assigning the get s to s variable, let's directly call the or lowercase on the return value of this method. And it says cannot invoke a string because returned value of because the return value of item 7, this is package.test1 class get s is null. So this is a very useful null pointer exception detail message, which tell you exactly where that null pointer happens. And we immediately understand that this is this method get s, which returns a null reference, right? The reference is null, and that's why we're getting a null pointer exception when we call this to lowercase on a null reference. All right. Okay, so now let's have a look at the example of the stack. So I'm going to create a new class called myStack. And if you're familiar with the data structures, a stack is more or less an abstract data structure, which means this is typically backed by another data structure or data type backed by another data structure. And here I'm going to back my stack with a array, right? Again, an array is something that the Java guarantees the existence of array as a rigid data type. So what I'm going to do, I'm not going to make it dynamic. I'm going to make a simple a stack which has a fixed size, right? And you so I'm going to say int size, and then I'm going to basically initialize it with, I don't know, 16. Sounds like a good number. So public myStack, and then int size, right? And then this dot size is size. So at the moment I'm not doing any I'm trying to make this stack class static, just as a simple example. So at the time of creation, So basically the size of the stack in fixed, and because I know the size, then I can basically obviously we can parameterize this on a type, right? But for now I'm going to say that this just holds integer numbers. Let's say this is an integer, which this is a stack that is specialized on integers. So int data, and then what happens here is that we're going to say that this data is in the at the time of construction. We're going to initialize with size, right? So note that the array types in Java only accept integers. They don't accept longs because it doesn't make sense. I mean, integer is 2 billion items, something like that, and beyond that you probably don't want such a very, very large array, especially of ints, which is 1 byte. So 2 billion bytes is how much is it? It's like 2 terabytes or something of just for one array. It doesn't make sense to have an array this large. All right, so this is a stack, and then what happens here is that we're going to push. Obviously a stack has two main method, right? So public, usually the push returns a boolean if the operation was successful, but I'm going to return void. So we're going to push int value. We're going to push something onto the stack, and then public void pop int value. And obviously this is going to return. Now, as you can see, at the moment, the things that we talked about item 7, about nulling out references, it doesn't really work that much well here because this is a primitive type. But I'm going to change this to the object type, right? So always note that, and obviously when we pop, we don't take anything. We're going to return an integer. So what happens here is that we create our data array. So our stack is our data structure, which is an abstract one, is backed by a real data structure, which is an array, which is guaranteed to exist by the language itself. And now what we're going at for the push, obviously we have to check a size. So we're going to have another pointer which call it pose or position, right? And we start at 0. And when we push something into the stack, and if so position starts from 0, so if obviously if position is greater than size, because the last index of this array is size -1, right? So if we are at size -1, we're still good, but if the position is beyond that, we're going to throw some exception, right? We can throw a runtime exception, throw or illegal state exception, illegal state exception, stack is full, right? So, and then if throw new, we should also, okay. And then note that this is a, I believe, runtime exception. It doesn't ask you to handle it by adding throws declaration here. So if the position or our stack is not full, what we're going to do is that we're going to say that this I don't need to use this here. Data at position ++ equals value, right? And then we simply return. Now, one way is to, instead of throwing exception, change the return type to Boolean, and here return false. And then if we don't run into this condition, we return true. That's also possible, right? Because sometimes you don't want the program to terminate. Maybe if the stack is full, you just want to not allow the operation, right? So we're pushing into the stack. At the beginning, the position is 0. So data at 0, we push it, and then the position becomes 1, right? Let's say size is 2, for example. And then the next time we push another one, we push position 1, and then position becomes 2, right? And then the next time push is called, we're going to throw an exception. So let's go and test this push operation. Let's say let's create a new class, test a stack. All right, and we're going to have a main method, and here I'm going to say my stack is new my stack. And again, at the time of creation of the stack, you have to specify what the size is. Let's say 2, and then a stack push integer 1. Again, the Java compiler takes care of auto boxing in this particular case because we're using a wrapper integer. And then a stack dot push 2. So let's run this. Nothing bad happens. What about if we stack dot push 3? Let's push 3. Let's see what happens. And we're getting a illegal state exception. Stack is full, right? So our push operation seems to work fine if up to the size we're pushing, and then after that we throw exception. All right. What about the pop? And the pop is where the item 7 basically comes into the picture. So I have a data structure. It's managing its own data, or basically objects, and the problem here is that this data is not an individual class. It's a class. Integer array is still an object, but it holds a collection of other references or references to other objects. And that's the problem, because at some point when we're popping, what happens here is that we're going to say integer obj is data at basically position minus minus, right? So right now where we are in the position, let's say we are at position 1. Obviously position was 2, so we have to basically put this here, right? So position advance to the next one, but when we're popping, we have to basically or maybe it's better to say position minus 1. Actually, we have to move the position anyways, right? And then and so in our example here, so at the beginning position is 0. After this position becomes 1. So pose is 1, and then here pose is 2. If I now start pop, I have to note that this index in the array is 1, right? So I have to pop from index 1, which is position minus 1. So we decrease the position. Obviously, we have to check if the position is 0, there is nothing to pop, right? So if position is basically so if position is basically less than 1, we can say, or basically less than 0, we're going to throw maybe illegal exception. A stack is empty. Stack is empty, and then return obj, right? So we're playing with the positions, because array of objects, array of references, integer array is not a dynamic type, it's a static type. So when it says it has 16 elements, you cannot change it at runtime, right? This array will always have 16 elements. We're just giving the illusion of the dynamicness to a stack by managing a pointer or a position indexing, right? So this is something that we are introducing. But then the problem is that this what happens when we go down. Obviously, if we push back something, we move forward, which is fine. The previous references that are not used anymore, they get replaced, and those are the other objects now are garbage collected. But if we just pop and then never push back, then there are references in the array that are not being used, but those references are still alive, right? So basically this does not kill the references. So let's have a look at here. So we push, and then we say that var a1 is stack.pop. Let's pop this, and then sysout a1, and then var a2 is stack.pop pop, and then sysout a2. Let's run this. 2 and 1, obviously 2 a stack is like last in first out, so 2 came out last, so it has to go first, right? So here pose becomes 1, and then here when we pop is pose becomes 0. And then what happens if we try to pop another one? Var a3 stack dot pop, and then sysout a3. So we're already throwing an exception, index -1 out of bounds for length 2. So where does this happen? It's here. So if position is exactly 0, so when position is 1 and we popping it, we basically means we're popping the index 0 in the array. So yeah, so let's see. Now it works. A stack is empty. So after this stack is empty, we're not doing anything. But the problem is that a stack is empty because we move this position index, but the references are not dead, right? The references are still alive. So if we pop, if the stack was 2 million items, we push a lot of items, 2 million items then, and we pop a few of them, but maybe we pop like I don't know, half of them, but although we pop them, they're still in this array, so they're still occupying memory. So what we need to do, we need to null the references. So after we get a hold of the reference in the array itself, right, we're going to say note that position has already changed, right? So we're going to say that position, just null it. And then I believe this code should still work just fine. We're not going to have any problem. Yes, but the difference now here is that if at each let's do a sysout arrays to a string, and then our data, right? Let's say whenever a and we can also do a basically whenever the push is successful, we're printing our array. Whenever the pop is successful, we're going to also print the array. So let's run this. So in the first, when we create the object, obviously it's a type of reference. So initial value or the default value for an object reference is null. So we push 1, the second one is still null. We push 2, and now we 2. We pop 1, we manually null the one that we pop, and then now null, right? And then we get this. So if we don't do this null, we are not careful about this memory leak, then as you can see, this item is still there. So there is a reference to this integer object on the Java heap, even though we popped it out of the stack, right? So that's it's what this item 7 is about.